Swayam Prabha. Digital India. Educated India.
Okay, in today's lecture what we will do is we will take few examples and solve using Rayleigh-Ridge method, and those examples includes eigenvalue problems, and also we will try with various trial solutions. So first to start with, let us take this differential equation or boundary value problem and solve using Rayleigh-Ridge method to obtain the approximate solution. And if you see this the problem statement, it is a second order differential equation, and the domain on which we need to solve, that is 0 to x, 0 to 1, x goes from 0 to 1, that is also given there. And since this is a second order differential equation, we require two boundary conditions to solve this one. So the two boundary conditions given are u evaluated at x is equal to 0 is 0, derivative of u, or the first derivative of u evaluated at x is equal to 1 is 1. And if you recall, using the thumb rule that I already gave you earlier, that is, if you have a differential equation of order 2p, those boundary conditions of order 0 to p are essential boundary conditions, and those boundary conditions of order p to 2p minus 1 are natural boundary conditions. So if you use that thumb rule, the first boundary condition you can easily verify it to be essential boundary condition, and the second boundary condition is what is called natural boundary condition. And also we will see here in the today's lecture why they are called essential and natural boundary condition in a different sense. Okay. So let us start with solving this problem using variational method or Rayleigh-Ridge method to obtain the equivalent functional. So the first step is the given differential equation we need to multiply with the variation of the quantity that we are looking for and integrate over the problem domain. Here the differential equation that is given is there given in the square brackets, and it is multiplied with the variation of u that we are interested in finding, or u is what is the quantity that we are interested in finding. So you multiply the given differential equation with variation of u, integrate over the problem domain. Limits of this integration should be from the limits of the domain. And the second step in obtaining the equivalent functional is integrate any term which has higher derivative, use integration by parts and reduce it to lower order derivatives. So the first, if you see this equation, the first term has second derivative of u, so we can somehow reduce this second derivative of u to first derivative of u by applying integration by parts to the first term. So that is what is done here. You just apply integration by parts to the first term, you get this term plus this term and this term, and these terms are as they are here, u times variation of u is already there, and also x square times variation of u is already there. Okay. And now this is the first step, or this is how you can reduce the order of differentiation, because that helps us in putting less demand on the continuity of the approximate solution that we are trying to use, or trial solution that we are trying to use. Now let us see the boundary conditions that are given. One of the boundary conditions that is given is variation of u evaluated at x is equal to 0 is 0, and these two terms, the first two terms can be we can actually simplify using some mathematical manipulations, and we will be using some variational identities here. If you see the first term, inside the integral you have this kind of quantity that can be rewritten in this manner. And also if you see our equation, we have this kind of quantity u times variation of u that can be written as 1 over 2 variation of u square, and also x square times variation of u, x acts like a constant, it is not going to be function of any of the coefficients. So x square times variation of u is it can be written as variation of x square u. So using these variational identities, the equation that you have earlier can be rewritten in this manner. And if you see this equation, somehow we need to eliminate these first two terms, so that we can put we can bring this into the form variation of some quantity inside the brackets is equal to 0, and this can be further simplified. Here you can see the inside the integral you have variation of second derivative of u square and variation of u square and variation of x square u, and half is like a constant. So this is like variation of u plus variation of v plus variation of w, and it is nothing but variation of u plus v plus w. So this entire thing can be put inside the variational operator, and this third part can be rewritten in this manner. Still we are left with the first two parts. Let us see how to cancel these two terms, first two terms. And to cancel the first two terms we use boundary conditions, and if you see the first term, this is the term that you have, and already natural boundary condition is given at this point, that is x is equal to 1. So substitute derivative of u with respect to x evaluated at x is equal to 1 as is given in the natural boundary condition, which is equal to 1. So the first term can be simplified to, when you make the substitution, it becomes variation of u evaluated at x is equal to 1. Okay. And if you see the other boundary condition, that is we need to evaluate at x is equal to 0, and already natural boundary condition is given, that is u evaluated at x is equal to 0 is 0. But what the problem is, it does not say anything about its derivative, and therefore this boundary term cannot be simplified to the form variation of some quantity inside. Okay. So the only way to proceed further is to assume a variation of u evaluated at x is equal to 0 is 0, which eliminates the second boundary term altogether, and we will see what is the implication of this. The implication of this assumption is that the trial solution for this problem must satisfy boundary condition at x is equal to 0 for any value of parameters. Please remember, at x is equal to 0 essential boundary condition is given. So the implication is at any cost you need to satisfy essential boundary condition, and so with this reasoning we can eliminate the second term also. So the first two terms get eliminated and you will be left with only the last term, that is variation of some quantity is equal to 0. So whatever is there inside the bracket, if you call that as I as a function of u, because if you see whatever is there inside the variational operator, everything is function of u. So I am defining a new quantity called I, which is going to be function of u, and that is what is called equivalent functional for this particular problem. So given any boundary value problem with the boundary conditions, you can adopt these steps to finally arrive at this kind of variational functional. Okay. Remember that this that in this functional the admissible trial solution are those that satisfy boundary conditions, that is u evaluated at x is equal to 0 is 0. They do not have to satisfy the boundary condition, that is natural boundary condition, that is derivative of u evaluated at x is equal to 1 is 1, because this boundary condition has been incorporated into the functional. Because of this reason, the first boundary condition is called essential, that is you need to satisfy at any cost, the trial solution has to satisfy at any cost, and the second boundary condition is called natural boundary condition or suppressible boundary condition. First boundary condition is also called required boundary condition, and you will understand better these once we look at one more problem, you will understand these better. So now let us start with quadratic polynomial trial solution. Okay. So let us say that we take a polynomial quadratic polynomial trial solution as u is equal to a naught plus a1x plus a2x squared. So now first job is before we proceed further, first job is to make this trial solution that we are starting with a admissible trial solution. To make the trial solution admissible, what we need to do is we have to make sure that this satisfies the essential boundary condition that is given for this particular problem. If you recall, the essential boundary condition that is given for this problem is u evaluated at x is equal to 0 is 0. So now to make this trial solution admissible, what you need to do is substitute this, that is u evaluated at x is equal to 0 is 0, that leads to a naught is equal to 0. Okay. So the admissible trial solution becomes a1x plus a2x squared. So now our job is to find what is this a1 a2, or what we will do is we will substitute, we will make this substitute, we will make this trial solution admissible trial solution, we will substitute into the equivalent functional and apply the stationarity conditions. And before we proceed further, we can check whether this admissible trial solution indeed satisfy the condition that variation of u evaluated at x is equal to 0 is 0 or not, because that is the condition that we use to eliminate one of the boundary term. So if you can just check the given admissible trial solution, you take variation of it and then substitute x is equal to 0, then it clearly satisfies the condition. Okay, and this is what is required for getting the equivalent functional. So now we have the admissible trial solution and we have the equivalent functional I as a function of u, and now u we are taking it as a1x plus a2x square. So you substitute, make the substitution of u into I, then I or the equivalent functional becomes a function of two unknown coefficients a1 and a2. And what we have is variation of I is equal to 0, that is possible only if partial derivative of I with respect to the unknown coefficients that you have in I, the partial derivative of I with respect to the unknown coefficients is equal to 0 independently. If you have n number of unknown coefficients, then the partial derivative of I with respect to each of these n unknown coefficients should be independently equal to 0. Here we have two unknown coefficients a1 a2. So the first stationarity condition is partial derivative of I with respect to a1 is equal to 0, and you already have I as a function of a1 a2, you take partial derivative of that with respect to a1 and equate it to 0, that gives you this first equation. And we have two unknown coefficients to be determined, so we need to get two equations. So how we get the second equation? Second equation can be obtained using the second stationarity condition, that is partial derivative of I with respect to a2 is equal to 0. Okay, so you got two equations both in terms of a1 a2, and you have two unknown coefficients to be determined. So you can solve these two equations, simultaneous equation for A1 A2. Solving the two equations simultaneously, we get the coefficients A1 A2 which are shown there. Now our job is over, we found what is A1 A2, and the admissible trial solution is A1x plus A2x square. So you substitute A1 value and A2 value, you get approximate solution for u, and if you want you can take derivative of this, because for this particular problem we know we can also easily calculate or we can easily find what is the exact solution for u, and also from there we can find what is the exact solution for derivative of u. So to make a comparison how approximate solution matches with exact solution, here what is shown is approximate solution of u is obtained by substituting A1 A2 coefficients into the admissible trial solution A1x plus A2x square, and taking derivative of it we get the second equation. So now this is what I mentioned, the exact solution for this particular problem can easily be verified. This is exact solution, and also from here if you take derivative of this with respect to x, you will get the first derivative. So now you have approximate solution for this problem and also exact solution for this problem, and let us see how they match. Approximate solution and exact solution are compared in the figure below, and here the approximate solution and exact solution are almost overlapping each other. So that is why you are unable to make any distinction between approximate and exact, but if you take the derivative you can clearly see some error is there in the approximate solution when compared to the exact solution. And please remember, whatever approximate solution that we got here is based on the quadratic trial solution that we started out with. Okay. So if you want to increase the accuracy, that means here already you can see that u value approximate and exact are almost overlaying on each other, but if you see the derivative of u there is some error. If you want to reduce this error you can go for higher order approximation. Okay. So you can start with cubic polynomial as a trial solution and follow the same process, that is you make sure before you proceed any more further, once you make assumption of some approximate trial solution, make sure that it is admissible by making sure that it satisfies the essential boundary conditions, and then using that admissible trial solution you plug that into the equivalent functional and apply the stationarity condition to get the unknown coefficients, solving the simultaneous equations that you get. So now what we will do is we will solve the same problem using cubic polynomial trial solution. Let us see whether the derivative, the error in the derivative, small error that we observed in the derivative can further be reduced. So let us start with cubic polynomial trial solution. You can easily guess that is nothing but a0 plus a1x plus a2x square plus a3x cube. Okay. So now first job is to make this admissible. Admissible means it has to satisfy essential boundary condition and impose that, that is you take this trial solution, substitute x is equal to 0 in that, then it leads to the condition that a0 is equal to 0. So the admissible trial solution becomes u is equal to a1 x plus a2x square plus a3x cube. Okay. So now your job is to find what is a1, a2 and a3. So what we will do is we will take this admissible trial solution and substitute into the equivalent functional that we already obtained using the various steps that are involved in variational procedure. That is, first step is multiply the given differential equation with variation of the quantity that you are interested, integrate over the problem domain, apply the integration by parts, reduce the order of the highest derivative appearing in the expression, and that is and apply the essential boundary condition, that is wherever essential boundary conditions are prescribed there variation of u is equal to 0, apply that condition, and also you substitute the natural boundary conditions and simplify using mathematical identities or sorry variational identities to bring it into the form variation of some quantity inside the bracket is equal to 0 and whatever is there inside the bracket, that is what is called equivalent functional. So that process is same even for whether you choose cubic polynomial trial solution or quadratic polynomial trial solution, that is all same, that is all not repeated here. Directly taking that equivalent functional, the admissible quadratic trial solution is substituted in the functional which we already have. Now the functional becomes a function of a1, a2 and a3, 3 unknown coefficients. Function of function is called functional, that you just remember, and now apply the stationarity condition. We got this equivalent functional variation of I is equal to 0, that is the condition that is satisfied if each of these conditions, that is partial derivative of I with respect to a1 is equal to 0, partial derivative of I with respect to a2 is equal to 0, partial derivative of I with respect to a3 is equal to 0 are satisfied. So here the first condition is applied, we got one equation and this results in this equation. Similarly you apply the other conditions, partial derivative of I with respect to a2 is equal to 0, you get the second equation, and there are 3 coefficients, unknown coefficients to be determined. So we require 3 equations, okay. You get the third equation by applying the third condition. So now you have the required number of equations for solving the 3 unknown coefficients. So you solve these 3 equations, solving the 3 equations simultaneously we can determine the unknown coefficients a1, a2, a3, the values are given there. So now next step is to substitute this a1, a2, a3 into the admissible trial solution we started out with, then you get the approximate solution, and by taking derivative of this you get the second equation that is given there, and then to see how the solution matches, approximate solution matches with exact, you can overlay the exact solution plot with this approximate solution. The approximate solution and exact solution are compared in the figure below. And now if you see, if you compare this with what you have seen earlier that we obtained using quadratic trial solution, the first derivative of solution is now much closer to the exact solution than with quadratic approximate solution, okay. So this is how you can increase the accuracy in the derivative quantity if you are interested, but it comes with some expense, that is you need to spend more, or you need to spend more computational effort, or it involves more calculations, okay. So now let us take another example. Here what we will do is, this example is similar to the previous example, but here what we will do is we will try using quadratic, cubic and quartic trial solution, that is 4th order trial solution, 4th order polynomial trial solution. So the boundary value problem that I am choosing is this one, that is second derivative of u with respect to x plus x square is equal to 0, that condition needs to be satisfied over the domain 0 to 1. Again this is second order boundary value problem, so we require 2 boundary conditions, and here mixed boundary conditions are given as given in the previous example, that is you have a combination of essential boundary condition and natural boundary condition. And also as in the previous example you can easily find the exact solution for this problem. You may ask me why I am, once we know the exact solution, why we are trying to find approximate solution. The logic is we will use various order of trial solutions and see how they match with exact solution, so that we can get an idea about the efficiency of this method. But the whatever technique we are learning here, that can be applied for some other problem where you do not have exact solution, that is the basic idea. So the first step is derivation of equivalent functional. So in that what we need to do is, the given differential equation we need to multiply with variation of the quantity that we are interested, that is u, and integrate over the problem domain, that is 0 to 1, okay. And here a new notation is used. I hope you are familiar with this. This is u double prime, it is nothing but second derivative of u. Usually this kind of notation is used to write the equation in a compact manner. And now highest derivative term is second order derivative. So what we can do is, we can reduce the order of derivative here u double prime to u single prime, that is first derivative of u, by using integration by parts over the first term. Do not disturb the second term, you apply the integration by parts for the first term, then that leads to this one. And once we get this, we need to think how to manipulate this using variational identities, and how to eliminate the boundary terms using the boundary conditions that are given. If not, if we cannot eliminate the boundary terms, what we can do is we can somehow manipulate them using variational identities, so that we can bring it this entire thing into the form variation of some quantity is equal to 0, okay. We will see those things. So first thing is, first term, that is from the natural boundary condition that is given, you have first derivative of u evaluated at x is equal to 1 is equal to 1 minus 2 times u evaluated at x is equal to 1, and what we can do is we can substitute directly this quantity into the previous equation, that results in the equation that is given here. And also we have the other condition, that is trial solution must satisfy essential boundary condition. What it means? It means wherever essential boundary condition is specified, at that point variation of u should be equal to 0. Therefore variation of u evaluated at x is equal to 0 is 0 for admissible trial solution, okay. So wherever essential boundary condition is prescribed, at that point variation of u is equal to 0. Here in this particular problem, essential boundary condition is prescribed at x is equal to 0, so variation of u evaluated at x is equal to 0 is 0. So the second term appearing in this equation becomes 0, you will be left with first term and the third term, that is what is shown here in this equation, okay. We cannot further more, we cannot eliminate any of the terms, because no more essential boundary conditions are given, but only thing is we can use some variational identities to simplify this. Already if you see the first term, sorry, the second term, if you see the second term, half is a constant, so you can, this is the first term is like variation of u, second term is like variation of v, so you can take the variational operator out, variation of u plus variation of v. So there is no need of much manipulations required for this term, only thing is we need to look into this. So let us look how can we write this one, and note that variation of u evaluated at x is equal to 1 minus u square evaluated at x is equal to 1, variation of this entire thing is nothing but variation of u evaluated at x is equal to 1 minus variation of u evaluated at x is equal to 1 square, okay. And this can be further written in this manner, and which is equal to this. So if you see the previous equation, this is a term you have. So what I am doing, what I am going to do is replace this term with this one, because both are equal. So then the previous equation becomes this one. So now you have what you want. What you want is, you want to bring the given problem into the form variation of some quantity is equal to variation of some quantity inside bracket is equal to 0. So that is what exactly you got it. So whatever is there inside the bracket, that is nothing but very equivalent functional, and everything in the bracket is function of u. So you can denote it with I as a function of u, that I is given by this is equivalent functional for this problem. Okay. So now once we get equivalent functional, what is the next step? Next step is we need to assume some trial solution. Here for this particular problem, what I will do is I will take three types of trial solutions. One is quadratic trial solution, cubic trial solution, and quartic trial solution, and show you the procedure. So several different approximate solutions for the boundary value problem are computed in the following sections. So first one is quadratic trial solution. So what I will do is I will start with quadratic trial solution, that is a naught plus a1x plus a2x square, and now by this time you can guess what is the next step. Make this trial solution admissible. To make this trial solution admissible, what you need to do? You need to substitute the essential boundary conditions that is given for this particular problem. So this is the reason why you should be good at identifying. If a boundary value problem is given with boundary conditions, you should be good at identifying which boundary condition is essential, which boundary condition is natural, because we need to make the trial solution admissible, we need to substitute the essential boundary condition before we proceed further. Okay. So the given quadratic trial solution, that is u is equal to a naught plus a1x plus a2x square, in that you substitute the essential boundary condition, that is u evaluated at x is equal to 0 is 1, that leads to the condition a naught is equal to 1. So your admissible trial solution becomes 1 plus a1x plus a2x square. Again here your job is to find what is a1 a2. If you find what are these unknown coefficients a1 a2, you can back substitute, or once you go through all the process, once you find the values, you come back to this equation, back substitute what is a1 a2 into it, and you will get the approximate trial solution, approximate solution for this problem. And before you proceed further, you can check whether earlier what we did is, to get the equivalent functional, we cancelled out the term variation of u is equal to 0. Variation of u evaluated at x is equal to 0 is 0. So to check whether that whatever we did is correct or not, now what you can do is, now you have the admissible trial solution, you take variation of it and substitute x is equal to 0, then you get variation of here variation of u evaluated at x is equal to 0 is 0. Okay. So that is how you can verify. So the substituting the admissible trial solution into the equivalent functional becomes a function of two unknown coefficients a1 and a2. Okay. All this is all similar to what we have done in the previous problem. So now variation of I should be equal to 0, that is possible only if partial derivative of I with respect to the unknown coefficients is equal to 0. These are the stationarity conditions. So apply that condition, you get the first equation, that is partial derivative of I with respect to a1 is equal to 0, and apply the second condition, that is partial derivative of I with respect to a2 is equal to 0, you get the second equation, and you got two equations, two unknowns a1 a2. You can solve for these two unknowns. Solving the two equations simultaneously gives us a1 a2, and what you can do is, once you get a1 a2, you go back to the admissible trial solution, that is 1 plus a1x plus a2x square. In that you substitute these coefficient values, you get approximate solution, and by forcefully taking derivative of it, you get the derivative of approximate solution. And one more thing, why the derivative quantity is not matching well with when we compared with exact solution. The reason is, it is important to note that since trial solutions did not explicitly satisfy natural boundary condition, whenever we are assuming what we did is, we started with a quadratic trial solution and we made that admissible by imposing the essential boundary condition, but we never imposed the natural boundary condition. So the point here is, it is important to note that since trial solution did not explicitly satisfy natural boundary condition, we do not expect the approximate solution to satisfy this condition exactly. Okay. So there will be some error when you take this, if you see the derivative quantity, that is what we observed even in the previous example, our u value is exactly matching with, or very accurately matching with the exact solution, whereas derivative of u, you have some error. Why it is so? Because we have not, the trial solution did not explicitly satisfy the natural boundary condition. Okay. So now how can we measure our accuracy, the solution accuracy? We can use this condition to check whether the quality of the approximate solution is good or not. So that is what it is mentioned there. We can use this, we can use the satisfaction of this condition, satisfaction of this condition refers to the natural boundary condition, as a check on the quality of the approximate solution. Okay. So what we can do is, we have the derivative of u here, you evaluate this derivative of u at x is equal to 1, and the natural boundary condition that is given is derivative of u evaluated at x is equal to 1 is 1, we see whether we get 1 or not. Substituting approximate solution into natural boundary condition, we get 1.1, actually we should get 1, means what, we got 10% error. We got 10% error. How we got it? We started with a quadratic trial solution. If you want to reduce this error further, what you can do is, you can start with higher order trial solution. You can go with, you can start with a cubic trial solution or a quartic trial solution. Okay. So now what we will do is, we will solve the same problem using cubic trial solution and see by how much percent this error reduces. And as we did earlier, we will just see how the approximate solution and the exact solution matches for the u and also derivative of u. That comparison is shown here. Here this is where 10% error is coming. So now let us solve the same problem using cubic trial solution. Cubic trial solution is a0 plus a1x, a2 plus a2x square plus a3x cube, and substitute the essential boundary condition into it, you get the admissible trial solution, which is 1 plus a1x plus a2x square plus a3x cube. Okay. Now you substitute this admissible trial solution into the equivalent functional. The equivalent functional remains same, whatever you already have, that is the equivalent functional for this problem. You do not need to repeat it again, only thing is we are changing the starting trial solution. So we have to, whatever trial solution you start out with, you have to make sure that it becomes admissible by substituting the essential boundary condition, make it admissible, and once you have the admissible trial solution, you substitute into the equivalent functional, then you get I as a function of the unknown coefficients. Here you have 3 number of unknown coefficients, that is a1, a2, a3, and you need to apply the 3 stationarity condition. I think by this time you know what are the stationarity conditions. you apply the stationarity condition, that is partial derivative of I with respect to A1 is equal to 0, you get one equation, partial derivative of I with respect to A2 equal to 0, you get another equation, partial derivative of I with respect to A3 is equal to 0, you get the third equation. So straightforward, we have 3 equations, 3 unknown coefficients, so we can solve for the 3 unknown coefficients A1, A2, A3, and once we get these the values of A1, A2, A3, you can go back to your admissible cubic trial solution and substitute in place of A1 whatever value you got here, A2 and A3, and then you get the approximate solution. And you can take you can forcefully take derivative of it, you get the derivative of approximate solution. Okay, and as I mentioned a few minutes back, the one way of checking the accuracy of solution is just check whether natural boundary condition is satisfied or not. Okay, so we got a derivative of u expression is given here. So what we can do is we can substitute in this equation x is equal to 1 and see what value we get, whether that value is how close it to 1. So whatever the difference in the closeness, that indicates the error in the approximation. In order to check the accuracy of solution, check natural boundary condition. You can see as expected cubic trial solution results in a less error, whereas quadratic trial solution you have 10% error, whereas cubic trial solution error became 1%. Okay, and you can further follow the same step and you can do the higher order trial solution approximation also. Here the plot is shown how the approximate solution first derivative are compared with exact solution for cubic trial solution. If you recall earlier with quadratic trial solution there is a lot of error here at this location and at this location, now the error got reduced. Okay, so now what we will do is we will repeat this problem with a 4th order polynomial or quartic trial solution. Again the story is same, that is you start out with some polynomial. Here we decided to go with 4th order polynomial, that is u is equal to a0 plus a1x plus a2x square plus a3x cube plus a4x power 4, and when you substitute the essential boundary condition, that is u evaluated at x is equal to 0 is 0, u evaluated at x is equal to 0 is 1, sorry, then that results in a0 is equal to 1. So then substitute a0 is equal to 1, you get the admissible 4th order trial solution. So here you need to determine 4 coefficients, unknown coefficients a1, a2, a3, a4. You substitute this into the equivalent functional, you get this. Equivalent functional became a function of 4 unknown coefficients. You know, you can easily guess what is the next step, apply the stationarity conditions. Partial derivative of I with respect to a1 is equal to 0, you get one equation, partial derivative of I with respect to a2 is equal to 0, you get the other equation, and similarly you get 2 more equations because we require in total 4 equations to solve for these 4 unknown coefficients. Third equation, fourth equation, and what you can do is you can solve the 4 equations simultaneously to get a1, a2, a3, a4, and what we need to do now is we need to substitute these coefficients into the trial solution, that is 1 plus a1x plus a2x square plus a3x cube plus a power a4 x power 4, and surprisingly what you observe is whatever approximate solution that you get is same as exact solution. So, in summary what we can say is, as we increase the order of the trial solution, we approach the exact solution, but at the expense of additional computational effort. Whenever you have more coefficients, what you are basically, you need to solve more number of equations to solve for this unknown coefficients. And what I will do is, I will show you next example on eigenvalue problem, and this is an eigenvalue problem. And why it is an eigenvalue problem? There if you see here this differential equation, you have one quantity lambda is there, because of that it becomes an eigenvalue problem, and this differential equation needs to be satisfied over the domain 0 to 1, and as you can guess this is a second order differential equation. So, we require two boundary conditions. The two boundary conditions for this problem are given here, and you can go back and check these two boundary conditions are essential boundary conditions, because this is a second order differential equation, and here lambda is the eigenvalue that needs to be determined. Okay. So, what we do is, do not get scared with this lambda appearing here, you just follow the regular steps to obtain the equivalent functional, and then you assume some trial solution, substitute the trial solution, apply the stationarity conditions, get the equation, solve for the unknown coefficients. All those steps are same. So, the derivation of equivalent functional proceeds in this manner: multiply differential equation by variation of the quantity that you are looking for, that is variation of u, integrate over the problem domain, and second order derivative is appearing, the first term has second order derivative. So, story is same, integration by parts you need to apply to reduce the order of derivative, and here we are very fortunate, because at x is equal to 0 and x is equal to 1 essential boundary conditions are prescribed. Essential boundary conditions are given at x is equal to 0 and x is equal to 1. So, automatically the first two terms, boundary terms, gets cancelled. Wherever essential boundary condition is given, variation of u at that point is equal to 0, or at least the variation of admissible solution at that point is equal to 0. So, the first two terms gets cancelled because of that reasoning. So, that is what is mentioned here. There are no natural boundary condition, therefore, for trial solution to be admissible we must require variation of u at x is equal to 0 is 0, variation of u at x is equal to 1 is 0. So, with that reasoning the first two terms gets cancelled and you will be left with this, and here also you can apply variational identities and bring the variational operator out. The variational identities you can use, or that is what is mentioned here. Using variational identities, the first term can be written in the manner given here, the second term can be written like this. Now it became like variation of u plus variation of v. So, we can bring the variational symbol operator out. Variation of u plus variation of v is nothing but variation of u plus v. So, the equivalent functional is nothing but whatever is inside the bracket. So, the equivalent functional is here. Equivalent functional is again, it is looking similar to what you have seen earlier, except that lambda is the additional quantity is lambda, but do not get scared, it becomes an eigenvalue problem. So, we will go with quadratic trial solution, and before we proceed further, what we need to do is we need to make this admissible, substitute the essential boundary condition, and then that results in a naught is equal to 0 and a1 turns out to be minus of a2. So, the admissible trial solution becomes a2 times minus x plus x square. Okay. So, now what you need to do is you take this admissible trial solution and substitute into the functional. Functional becomes a function of only one coefficient, unknown coefficients only one unknown coefficient a2, and what is the stationarity condition? Partial derivative of I with respect to a2 is equal to 0, that results in one equation, one unknown. And if you see this equation, a2 times minus 10 plus lambda is equal to 0, this is what an eigenvalue problem is. Here a2 cannot be 0, because if a2 is 0, actually all these coefficients a0, a1, a2 are all non-zero coefficients, and a2 cannot be 0, and only way this equation can be 0 is lambda should be equal to 10, and a2 is equal to 0 is a trivial solution, but we are looking for non-trivial solution. So non-trivial solution leads to the thing that lambda is equal to 10. So the approximate first eigenvalue for this problem is 10, okay, and you can, as we did for the previous problems, what we can do is we can start out with a cubic trial solution. We will go through this process quickly. Start with a quadratic, here it should be cubic. Start with a cubic trial solution, a0 plus a1x plus a2x square plus a3x cube, and substitute the essential boundary conditions, and that leads to a0 is equal to 0, a1 is equal to minus a2 minus a3. So the admissible trial solution becomes a2 times minus x plus x square plus a3 times minus x plus x cube, and substitute this admissible trial solution into the functional. Functional is going to become a function of unknown coefficients a2 and a3, okay. So you got this as a function of a2 and a3. Next step is apply the stationarity conditions. Two equations, two unknowns. You can put this in a matrix form. These two equations can be put in a matrix form, and if you see this equation system, how it is looking? It is looking like a minus lambda b times x is equal to 0, which is a eigenvalue problem. For non-trivial solutions, that is non-zero value of a2, a3, means non-zero value of that vector a2, one of them can be 0, but both of them cannot be 0. So for non-zero value of that a2, a3 vector, the condition is for non-trivial solution, a minus lambda times b, determinant of that should be equal to 0, which results in a characteristic equation of order, if it is a 2 by 2 matrix system, you will get a characteristic equation of order 2, which when you solve you get 2 roots, and those roots gives you the first eigenvalue